When you make decisions, there is a systematic way that you can approach it. Business analytics is all about making better decisions, so what we want to do is we want to study decision analysis. It can be used to develop an optimum strategy, and it's done when a decision maker is faced with several decision alternatives and an uncertain or risk-filled pattern of future events. That's the setup for using decision analysis. An example of this is the state of North Carolina, my home state, used decision analysis in evaluating whether to implement a medical screening test to detect metabolic disorders in newborns. A good decision analysis includes careful consideration of risk. So when we get into decision analysis, we want to make sure we understand risk and we want to quantify and qualify risk in order to make the very best decision. Risk analysis helps to provide the probability information about favorable as well as unfavorable outcomes that may occur. Decision analysis considers problems that involve reasonably few decision alternatives and reasonably few possible future events. In order to engage in decision analysis, we have to first deal with problem formulation. The steps include problem formulation, creating a verbal statement of the problem, and identifying the decision alternatives. The alternatives include any uncertain future events, referred to as chance events, and the outcomes associated with each combination of decision alternative and chance event outcome. Here's an example we want to use as we further get into decision analysis. PDC commissioned a preliminary architectural drawing for 3 different projects, one with 30 condominiums, one with 60 condominiums, and one with 90 condominiums. The financial success of the project depends on the size of the condominium complex and the chance event concerning the demand for the condominiums. The statement of the PDC decision problem is to select the size of the new luxury condominium project that will lead to the largest profit given the uncertainty concerning the demand for the condominiums. Given the statement of the problem, it is clear that the decision is to select the best size for the condominium complex. PDC has the following 3 decision alternatives. Decision 1, or D1, is to build a small complex of 30 condominiums. Decision 2, or D2, is to build a medium complex of 60 condominiums. Decision 3, or D3, is to build a large complex of 90 condominiums. In decision analysis, the possible outcomes for a chance event are the states of nature. States of nature are mutually exclusive, no more than one can occur, and collectively exhaustive, at least one must occur. Thus, one and only one of the possible states of nature will occur. It is basically like flipping a coin. You're either going to get heads or you're going to get tails. You're not going to get any other choice. So your choices and that chance event are mutually exclusive, heads or tails, and collectively exhaustive. It has to be heads or tails. In the PDC example, the chance event concerning the demand for the condominiums has 2 states of nature. The first state is strong demand for the condominiums, and then the second state is weak demand for the condominiums. So it's either going to be strong or weak demand, no in between. As a part of problem formulation, one of the things we have to consider is payoff tables. Payoffs are the outcome resulting from a specific combination of a decision alternative and a state of nature. A payoff table is a table showing payoffs for all combinations of decision alternatives and states of nature. Table 12.1 gives us an example of a payoff table. We're going to use this for our example, the PDC condominium project. As you see in the table, you have 3 decision alternatives. Small complex, 30 condominiums, that one is D1. Medium complex, 60 condominiums, that's D2. And large complex, 90 condominiums, that's D3. Those are our alternatives. And then to the right, you see the states of nature. Strong demand, 8, 14, and 20 is what's represented there. Weak demand, 7, 5, and -9. We'll get into what those are in a little bit. For our example, we will use the notation V sub I sub j to denote the payoff associated with decision alternative I and state of nature J. Using the table, V sub 3(1) equals 20 indicates that a payoff of $20 million occurs if the decision is to build a large complex D3 and a strong demand state of nature S1 occurs. As a part of problem formulation, we build out what's called a decision tree. The decision tree provides a graphical representation of the decision-making process. It shows the natural or logical progression that will occur over time. For example, the topmost payoff of 8 indicates that an $8 million profit is anticipated if PDC constructs a small condominium complex, D1, and demand turns out to be strong. In Figure 12.1, we see an example of a decision tree. As you look at this figure, you see the 3 decision alternatives, small, medium, and large, to the left. And for each one of those decision alternatives, you see the states of nature, strong and weak, to the right. The numbers that you see represent the payoff that you would receive if you chose small as a decision and the state of nature is strong, for example, that would be equal to 8. You can see all of the payoffs for each decision in a decision tree. The decision tree in the figure shows something called a node. And what a node is, it's used to represent decisions and chance events. There are 4 nodes numbered 1 through 4 in that figure, and each of those nodes represents the decision and chance event combination. Squares are used to depict decision nodes. Circles are used to depict chance nodes. Thus, node 1 is a decision node, and nodes 2, 3, and 4 are chance nodes. Branches connect the nodes, and those leaving the decision node correspond to the decision alternatives. The branches leaving each chance node corresponds to the state of nature. The outcomes, or the payoffs, are shown at the end of the state of nature branches. Everything we just talked about, from branches to nodes to decisions and states of nature, are all put together in a graphical form to show you a representation we would call a decision tree. We will use decision trees as one of our tools to complete decision analysis throughout the course. Let's talk about decision analysis without probabilities. And then we'll talk about decision analysis with probabilities. Decision analysis without probabilities is appropriate in situations in which a best simple case and worst case analysis is sufficient, or where the decision maker has little confidence in his or her ability to assess the probabilities. There are not a lot of very involved math people out there who understand statistics and probabilities and inference. So if you have to complete a decision analysis, sometimes you have to do it without probabilities. So we're going to talk about how to do that in the next few minutes. One way to do it is to approach the problem optimistically and then pessimistically. So let's talk about the optimistic approach. The optimistic approach evaluates each decision alternative in terms of the best payoff that can occur. The decision alternative that is recommended is the one that provides the best possible payoff. So in the PDC problem, the optimistic approach would lead the decision maker to choose the alternative corresponding to the largest profit. For minimization problems, this approach leads to choosing the alternative with the smallest amount of payoff. If you look at table 12.2, let's look at the maximum payoff for each decision alternative. If the company chose the small complex, 30 condominiums, the maximum payoff would be $8 million, represented by the number 8. If they chose the medium complex of 60 condominiums, then the maximum payoff would be $14 million. If they chose the large complex of 90 condominiums, then the maximum payoff would be $20 million. Now, you can also take a conservative approach to this. You can evaluate each decision alternative in terms of the worst payoff that can occur. And the decision alternative recommended is the one that provides the best of the worst possible payoffs. In the PDC problem that we're studying, the conservative approach would lead the decision maker to choose an alternative that maximizes the minimum possible profit that could be obtained. For problems involving minimization, for example, when the output measure is cost, and we did a little bit of a minimization example earlier in the course, this approach identifies the alternative that will minimize the maximum payoff. So in table 12.3, we see the minimum payoff for each of the PDC decision alternatives. If they build a small complex of 30 condominiums, then the maximum of the minimum payoff would be $7 million. If they choose to build the medium complex of 60 condominiums, then the maximum of the minimum payoff would be $5 million. Last but not least, if they choose to build the large complex of 90 condominiums, then the maximum of the minimum payoff would be negative $9 million. So if they build the large complex, then they have a chance of actually losing money versus making money. Let's talk about the minimax regret approach. What is regret? I think we all have in life experienced some form of regret. It actually happens in decision analysis as well. A regret is the difference between the payoff associated with a particular decision alternative and the payoff associated with the decision would yield the most desirable payoff for a given state of nature. Regret is often referred to something we all are familiar with, opportunity cost, but in this case, we're going to define it as opportunity loss. Under the minimax regret approach, one would choose the decision alternative that minimizes the maximum state of regret that could occur over all possible states of nature. How do we figure out regret for a problem like this? Equation 12.1 gives us the view of what regret looks like mathematically. The regret associated with decision alternative DI and state of nature SJ, we're going to call that RIJ, that is equal to the absolute value of the payoff value corresponding to the best decision for the state of nature SJ, we're going to call that V star sub J, that minus the payoff corresponding to the decision alternative DI and state of nature SJ, and we're going to call that V sub IJ. We're going to take the absolute value of that difference, and that is what's going to be equal to your regret or opportunity loss. Using the equation in 12.1 and the payoffs in table 12.1, the regret associated with each combination of decision alternative DI and state of nature SJ is computed. To compute the regret, subtract each entry in a column from the largest entry in the column. So if you look at table 12.4, you see the regret or opportunity loss for each of the decisions. If they decide to build a small complex, 30 condominiums, the strong demand regret is 12 million. The weak demand for that same decision is 0 million. For the medium complex or the 60 condominium project, the strong demand says that the regret would be 6, and the weak demand for that same decision is 2. Last but not least, if they choose to build the large complex, 90 condominiums, if they have strong demand, then the loss is 0. But if they have weak demand, then the loss is going to be 16 million. So this is another way to build your decision tree out to figure out which decision you should go with. Table 12.5 shows you the maximum regret for each of the decision alternatives. So the maximum for the small complex is 12 million, the medium complex is 6 million, which is the minimum of the maximum regret. And then the large complex regret would be 16 million. In our decision analysis process, the next step in applying the min-max regret approach is to list the maximum regret for each decision alternative. For the PDC problem, the alternative to construct the medium condominium complex with a corresponding maximum regret of $6 million is the recommended min-max regret decision. Another approach that we can take in decision analysis is the expected value approach. The expected value of a decision alternative is the sum of weighted payoffs for the decision alternative. The weight for a payoff is the probability of the associated state of nature and therefore the probability that the payoff will occur. Figure 12.2 shows the decision tree for the PDC problem with state of nature branch possibilities. Now, if we look at the equation 12.2, which is the expected value of decision alternative D sub I, it is equal to the summation of the probabilities of the states times the payoffs for the decision and the related state. That is what that equation means. EV D sub I is equal to the summation of J from I to N of P state, which would be S sub J, times the payoff, which would be V I J. If we look at figure 12.3, we're looking at the expected value approach of the decision tree for the PDC condominium project. For each of the decision alternatives, small, medium, large, complex, you see the expected value there for each branch. Now let's approach decision analysis with probabilities. Up to now, we dealt with the problems without probabilities and using our best approach to get to a decision. Now we're going to approach the same problem using probabilities. To do that, you have to select the decision branch leading to the chance node with the best expected value. The decision alternative associated with this branch is the recommended decision. In practice, obtaining precise estimates of the probabilities for each state of nature is often impossible. So historical data is preferred to use for estimating the probabilities for the different states of nature. Now we can talk about risk analysis. Risk analysis helps the decision maker recognize the difference between the expected value of a decision alternative and the payoff that may actually occur. Decision alternative and the state of nature combine to generate the payoff associated with a decision. Risk profile. That is for a decision alternative, and it shows the possible payoffs along with their associated probabilities. If you look at figure 12.4, this is the risk profile for the large complex decision alternative for the PDC condominium project. You see two lines. You see 20 million in profit, and then you see negative 9 million in profit according to this figure. What you also see is for each of those alternatives, the probability that that may occur. In observing this diagram, you have an 80% chance of making $20 million, which is what this shows, versus a 20% chance of making negative 9 or losing $9 million. So this is the risk profile for just that one decision. When we approach the expected value analysis of our decision analysis process, this is how we would approach it. Another type of analysis that we can do when we have probabilities is the sensitivity analysis. This determines how changes in the probabilities for the states of nature or changes in the payoffs affect the recommended decision alternative. In many cases, the probabilities for the states of nature and the payoffs are based on subjective assessments. So sensitivity analysis helps the decision maker understand which of these inputs are critical to the choice of the best decision alternative. If a small change in the value of one of the inputs causes a change in the recommended decision alternative, the solution to the decision analysis problem is sensitive to that particular. Let's take a look at an example. Using the PDC data that we have, suppose that in the PDC problem, the probability for a strong demand is revised to 0.2 or 20%, and the probability for a weak demand is revised to 0.8 or 80%. Here's how the expected values change. So the expected value of decision 1, build the small complex, now becomes $7.2 million in profit. The decision to build the medium complex, 60 condominiums, now changes to $6.8 million. And the last decision, the decision to build the large complex, now changes to $23.2 million. With these probability assessments, the recommended decision alternative is to construct a small condominium complex with an expected value of $7.2 million. Thus, when the probability of strong demand is large, PDC should build the large complex. When the probability of strong demand is small, PDC should build the small complex. That's how we leverage the expected value approach in this problem. In conclusion, building decision trees using alternatives, states of nature, and probabilities, those are the things you're going to use in decision analysis problems. And it's basically designed for you to figure out which decision is the best decision based on what you know.